The metalloids reside between the metals and nonmetals on the periodic table. They exhibit some qualities of metals and nonmetals. Many metalloids act as semiconductors by behaving as electrical insulators at room temperature, but electrical conductors when heated. This property is vital to the computer industry. Boron is a yellow-brown crystal. This non-metallic element is used to make high-strength and lightweight aerospace equipment. When it burns, boron gives off a distinctive green glow, so it is a main element in green fireworks and flares. Silicon is a hard, dark non-metal. It is the second most abundant element and makes up 25% of the Earth's crust. A large part of sand, clay, granite, and quartz is silicon. This useful element goes into solar cells, tools, cement, grease, and perhaps most importantly, semiconductors and computer microchips. Germanium also goes into computers and electronics. This hard, brittle, gray-white metal is used to make transistors, semiconductors, infrared optical instruments, and wide-angle camera lenses. Arsenic is a gray, brittle non-metal. It is a deadly substance that has been used to make rat poisons and insecticides. It is also used in the manufacture of metal alloys, mirrors, glass, lasers, and semiconductors. Arsenic is a byproduct of copper forging, and it could provide evidence about when our ancestors began to make copper tools. Antimony is a hard and brittle blue-white metal that is a poor conductor of heat and electricity. It helps make lead alloys more durable, and it goes into flame-proofing materials, lead batteries, mascara, paints, glass, pottery, and plastics. Tellurium is a silver-white metal-like non-metal. Small amounts of this element are added to copper and stainless steel alloys to make them easier to work with. It also colors glass and ceramics. The rare radioactive metal polonium is used to make nuclear batteries. It is currently under consideration as a possible heat source on spacecraft. Small amounts of polonium are used in shielded brushes that remove dust from photographic film. The metalloids are a diverse collection of elements. Most are brittle, somewhat shiny solids that exhibit properties of metals and nonmetals. Some of them, such as antimony, have the appearance and luster of metals. But others, such as arsenic, clearly appear to be nonmetals. Their chemical properties range between those of metals and nonmetals. One of the most unique properties is semiconductivity. Acting like nonmetals, semiconductors block electric currents at room temperature. But when they are heated, they act like metals, allowing electricity to flow through them. This unique property makes the metalloids, particularly silicon and germanium, valuable to the computer and electronics industries, where semiconductors are used in everything from calculators to computer chips. The unusual appearance and behavior of the metalloids can be explained by taking a closer look at the periodic table. On the periodic table, the elements are listed in order of their atomic number. The atomic number represents the number of protons in an element's nucleus. In its normal ground state, this nucleus is also surrounded by an equal number of electrons. As you read the periodic table from top to bottom, each horizontal line is called a period. Each period represents the number of electron shells the element's atoms normally have. For example, there are 4 electron shells in an atom of germanium, so it lies in period 4. Meanwhile, an atom of polonium, in period 6, has 6 electron shells. Each of these shells can contain up to 8 valence electrons. As you read the table from left to right, the vertical lines of elements are called groups. Elements in one group have the same number of valence electrons in their outermost electron shells. If an element has 8 valence electrons, as the noble gases do, Its outermost shell is completely filled, and the element generally does not react chemically with other elements. If an element has less than 4 valence electrons in its outermost shell, as most metals do, it is electropositive, which means it tends to give up its valence electrons to other elements during chemical reactions. If an element has more than 4 valence electrons, as nonmetals do, it is electronegative, which means it grabs electrons from other elements during reactions to fill its outermost shell. The metalloids form the line that runs between the metals and nonmetals on the periodic table. They span groups 13 through 16 and have anywhere between 3 and 6 valence electrons. The atomic structures of the metalloids lie squarely between those of the metals and nonmetals. For example, boron has 3 valence electrons and usually acts as a metal by shedding its valence electrons during chemical reactions. Arsenic, antimony, tellurium, and polonium have more than 4 valence electrons, and they typically act as nonmetals by gaining electrons from other elements. Meanwhile, silicon and germanium, with exactly 4 valence electrons each, sometimes act as metals and other times as nonmetals. The metalloids and their great variety of properties are valuable for many industrial materials, from transistors and semiconductors to ceramics, solar batteries, and certain polymers. The metalloids may be the strangest and most useful of all the element groups on the periodic table.
Element number 5 on the periodic table is boron. The atomic symbol for boron is B. Boron is a nonmetallic element that can be a dark brown or black powder, or a very hard yellow-brown crystal. Boron gets its name from borax, a naturally occurring compound that contains the element. Boron is classified as a metalloid and lies in the periodic table's second row, called period 2. Each atom of boron consists of a cloud of electrons surrounding a compact nucleus that contains almost all the atom's mass. In the most common form of boron, the nucleus has 5 positively charged protons, plus 6 uncharged neutrons. Boron has 5 negatively charged electrons to balance its 5 protons. These electrons are found in 2 shells surrounding the nucleus, which can be visualized as being built up from the nearest preceding noble gas, helium. Helium has 2 electrons distributed in a single electron shell. The 3 additional electrons in boron determine its unique chemical behavior. 2 of these electrons are found in a spherical 2s orbital shell. The remaining electron is found in one of 3 lobe-shaped 2p orbitals. Boron will typically share, rather than lose, its electrons by forming covalent bonds with other elements. Boron is shown here in its black crystalline form, being picked up with forceps and placed in a clear hydrogen flame. When the boron enters the flame, it produces a brilliant green glow. Boron is often used in fireworks and other such devices because it burns with this attractive bright green flame. Boron's melting point is very high, over 4,000 degrees Fahrenheit. So while the piece of boron colors the flame, it does not melt. Boron fibers are very strong, and they can be added to plastics to make materials that are stronger than steel, yet lighter than aluminum. Boron compounds are also used in fireworks and flares, fiberglass, various household products, and heat and radiation-resistant alloys. Anyone who has ever attended a 4th of July celebration knows how thrilling a great fireworks display can be. But the next time you are oohing and aahing over a fireworks show, remember that you are also watching a spectacular display of elements in action and the wonderful effects that chemists can create.
To produce a fireworks effect, the first thing you need is heat. So the fireworks chemist prepares a mixture that has an oxygen-rich chemical and a fuel, and that will burn when it's ignited.
But the heat and burning is only half the story. What gives fireworks their brilliant colors are the chemicals placed inside the firework shell. For example, when the element boron is exploded in a firework, it gives off a green glow. And every element gives off its own unique color. Chemists use this fact to create spectacular results in the sky and the lab.
For example, if you add a strontium compound, you will produce a beautiful red flame color. If instead you use a copper compound, you can achieve a blue flame. Yes, that's it.
The color an element produces depends on the wavelengths of light it emits while burning. When an element such as charcoal radiates wavelengths across the entire visible spectrum of 380 to 780 nanometers, it will appear white. Elements such as boron emit wavelengths from a much smaller portion of the visible light spectrum. Burning boron, or barium, emits wavelengths in the 500 nanometer range and gives off a striking green light. Chances are, when you see green fireworks exploding majestically above you, boron or barium is responsible. Chemists use their knowledge of the elements and the light spectrum to create these spectacular effects. Yellow fireworks contain sodium. Calcium salts give off an orange glow. Strontium or lithium glow red. When bright white light is needed, chemists turn to aluminum, magnesium, or titanium.
So the chemist develops these materials and then really turns them over to the fireworks artist. Says, here are your paints, you go light up the sky with them. And this blend of science and art is what makes fireworks so fascinating.
The result, beautiful, blinding, breathtaking fireworks. All brought to you by boron and a collection of other equally exciting elements.
Element number 14 on the periodic table is silicon. The atomic symbol for silicon is Si. Silicon is a hard metalloid that can take the form of a brown shapeless powder or a dark gray crystal. Silicon gets its name and atomic symbol from the Latin word silex, which means flint or hard stone. Silicon is classified as a metalloid, and it lies in the third row of the periodic table, called period 3. Each atom of silicon consists of a cloud of electrons surrounding a compact nucleus that contains almost all the atom's mass. In the most common form of silicon, its nucleus has 14 positively charged protons plus 14 uncharged neutrons. Silicon has 14 negatively charged electrons to balance its 14 protons. These electrons are found in 3 shells surrounding the nucleus, which can be visualized as being built up from the nearest preceding noble gas, neon. Neon has 10 electrons distributed among its 2 electron shells. Silicon has 4 more electrons than neon. The first 2 electrons are found in the sphere-shaped 3s orbital shell. The remaining 2 electrons are found in 2 of the 3 lobe-shaped 3p orbitals. It is these 4 valence electrons that determine how silicon interacts with other elements. Silicon dioxide is the main ingredient in quartz and borosilicate glass. Borosilicate glass is widely used for laboratory glassware because it has excellent thermal properties and is resistant to attack from water, acids, salt solutions, organic solvents, and halogens. But when borosilicate glass is heated and then rapidly cooled in cold water, the thermal shock causes the rod to shatter. Quartz glass, which is pure silicon dioxide, is far more resistant to thermal shock than borosilicate glass. Quartz glass has a very high melting point, over 1800 degrees Fahrenheit. When quartz glass is heated and plunged into cold water, the rod remains perfectly intact. Silicon is the second most abundant element on the planet. Compounds of silicon are used to manufacture glass and to make soaps, adhesives, egg preservatives, lubricants, polishes, electrical insulators, cement, and solar cells. Very pure silicon is used to make semiconductors and microchips for electronic devices. We are living in a revolutionary time in human history. We have moved from the industrial era to the age of information, and the revolution has occurred thanks to the computer. You can find computers almost everywhere, from high-performance jet fighters to Buddhist monasteries in remote Indian villages. Today, computers are essential to most parts of our lives. But computers are little more than super-fast calculators. They work by reducing everything in the world to numbers. Computers perform their calculations using binary numbers, strings of ones and zeros that can represent every other possible number. Binary numbers are like an array of light bulbs, each connected to a light switch. Depending on which bulbs you turn on or off, you can spell anything. The first computers relied on mechanical on-off switches. But early researchers soon switched to vacuum tubes, which did the same thing, but faster. When the current was flowing through the tube, it acted as a binary 1. When the current stopped, it was a 0. But everything changed with the discovery that silicon acts as a semiconductor. At high temperatures, semiconductors conduct electricity as if they were metals. But at lower temperatures, they act as insulators, stopping electric currents from flowing. This unique property enabled researchers to create silicon transistors without moving parts that allowed a current to pass through or not, depending on their temperature. Now, binary switches could be microscopic, faster, and more reliable. Silicon transistors revolutionized and miniaturized the world of computers. Like a huge collection of factory workers, millions of transistors could be linked in microscopic assembly lines inside a single silicon chip, all switching on and off in fractions of a second, and all translating binary numbers into letters, symbols, pictures, and all the other information that we rely on every day.
Element number 32 on the periodic table is germanium. The atomic symbol for germanium is Ge. Ultra-pure germanium is a silvery white, brittle, semi-metallic element that is highly reflective of light. The name germanium is derived from the Latin word for the country Germany, where the element was discovered in 1886. Germanium is classified as a semi-metal, or metalloid. It is located in the periodic table's fourth row, period 4. Each atom of germanium consists of a cloud of electrons surrounding a compact nucleus that contains almost all of the atom's mass. In the most common form of germanium, its nucleus has 32 positively charged protons, plus 41 uncharged neutrons. Germanium has 32 negatively charged electrons to balance its 32 protons. These electrons are found in 4 orbital shells surrounding the nucleus, which can be visualized as being built up from the nearest preceding noble gas, argon. Argon has 18 electrons distributed among 3 orbital shells. Germanium has 14 more electrons than argon. The first 2 electrons are found in the sphere-shaped 4s orbital shell. The next 10 electrons fill 5 clover-shaped 3d orbitals. The remaining 2 electrons are distributed in 2 of 3 lobe-shaped 4p orbitals. Since the electrons in the 3d orbital are at a lower energy than those in the 4s and 4p orbitals, only the 4 valence electrons in the 4th level shell influence how germanium interacts with other elements. Because germanium is transparent to infrared energy, but not light, it is an ideal material to make the lens of an infrared camera as shown here. Infrared images are based on heat instead of visible light. When the lens is held up to the person's face, we are able to see an infrared image of the man's face transmitted through the camera, even though the lens blocks visible light and appears black to the naked eye. The most common use of germanium today is in semiconductors. Germanium alloys are also used to make transistors and in dentistry. Germanium is used in infrared cameras and other types of optical equipment, and germanium is currently being studied for a possible use in chemotherapy. Element number 33 on the periodic table is arsenic. The atomic symbol for arsenic is As. Arsenic is a highly poisonous metallic element that is commonly found as a brittle, steel-gray crystalline solid that tarnishes quickly in air and smells of garlic when heated. Arsenic is classified as a metalloid, and it lies in the periodic table's fourth row, period 4. Each atom of arsenic consists of a cloud of electrons surrounding a compact nucleus that contains almost all the atom's mass. In the most common form of arsenic, its nucleus has 33 positively charged protons plus 42 uncharged neutrons. Arsenic has 33 negatively charged electrons to balance its 33 protons. These electrons are found in 4 orbital shells surrounding the nucleus, which can be visualized as being built up from the nearest preceding noble gas, argon. Argon has 18 electrons distributed among 3 orbital shells. Arsenic has 15 more electrons than argon. The first 2 electrons are found in the sphere-shaped 4s orbital shell. The next 10 electrons fill 5 clover-shaped 3d orbitals. And the final 3 electrons are distributed among 3 lobe-shaped 4p orbitals. Since the electrons in the 3d orbital are at a lower energy than those in the 4s and 4p orbitals, only the 5 valence electrons in the 4th level shell influence how arsenic interacts with other elements. Arsenic is stable in dry air, but the surface oxidizes slowly in moist air to produce a dark covering over the element. Arsenic and its compounds are very poisonous, and contact with the skin can cause skin cancer. So arsenic must be handled extremely carefully with gloves. In this experiment, arsenic is placed into a 30% solution of hydrogen peroxide. The arsenic reacts by bubbling and fizzing, and the dark oxide layer is dissolved, revealing the silvery pure element beneath. Arsenic is a deadly poison that can also cause cancer. It is primarily used to make insecticides and animal poisons. Small amounts of arsenic can be added to metal alloys to help make them stronger. Arsenic is also used in the manufacture of mirrors, glass, LED lights, lasers, and semiconductors. In 1991, an extraordinary archaeological discovery occurred in the Alps on the border of Austria and Italy. Buried in the snow of a mountain pass were the remains of a man who lived 5,000 years ago. He was the oldest frozen mummy ever found. Scientists called him Ötzi, the Iceman. By carefully examining his body and the items found with it, researchers have pieced together glimpses into the Iceman's past. One of Ötzi's possessions was a copper axe. The axe stunned scientists. Before its discovery, they thought copper tools had not been invented until 500 years after the Iceman's death. This axe has made a greater impact than any other item found with the body. And researchers from Oxford University believe samples of the Iceman's hair and the elements it contained suggest he had the skills to make such a tool.
We found copper particles on the surface, and when we sliced the hair, we found that the copper was indeed localized quite strongly on the surface of the hair. And we also found arsenic, which is equally unusual, and that's not a traditionally, that's not found in normal human hair to the detection limits of our instrument, you don't usually see any arsenic.
So Ötzi's hair was covered in copper and dangerously high levels of arsenic. But how did the arsenic get into his hair? Perhaps after the Iceman died, he and his belongings were contaminated by elements in the soil around them. So the Oxford team carried out the same tests on deer hair found in some of the artifacts.
If you assume that the basic structure of the deer hair and human hair is similar, then any contaminants in the local environment will be absorbed equally by the deer hair and the human hair. But in fact, we found that the deer hair contained relatively small levels of copper and no arsenic. These are unusually high copper levels for natural contamination. He would have had to have been buried in the outflow from a copper mine or something to have obtained copper levels like this.
So the Iceman must have been exposed to copper and arsenic while he was alive for his hair to have absorbed them. This would be the case if the Iceman had been involved in making copper objects, such as his axe. Copper can be extracted from malachite, a green stone that contains copper ore. But much of the malachite in this part of the world also contains arsenic. Early toolmakers crushed malachite and smelted it to produce their copper. But this process also released arsenic vapor. As the toolmakers worked, they would be exposed to high levels of arsenic, just like those found in Ötzi's hair. So scientific evidence seems to indicate that the Iceman spent at least some of his days making copper tools. This knowledge gives modern researchers a glimpse into how Ötzi lived 5,000 years ago, and it was provided by the deadly element arsenic.
Element number 51 on the periodic table is antimony. The atomic symbol for antimony is Sb. Antimony is shown here in its metallic form, which is bright and silvery, hard and brittle. The name antimony most likely came from the Greek word antimonos, meaning opposed to solitude. The symbol for antimony is an abbreviation of stibium, the Latin name for one of its common and better known compounds. Antimony is classified as a metalloid. It lies in the periodic table's 5th row, period 5. Each antimony atom consists of a cloud of electrons surrounding a compact nucleus that contains almost all the atom's mass. In the most common form of antimony, its nucleus has 51 positively charged protons, plus 71 uncharged neutrons. Antimony has 51 negatively charged electrons to balance its 51 protons. These electrons are found in 5 orbital shells surrounding the nucleus, which can be visualized as being built up from the nearest preceding noble gas, krypton. Krypton has 36 electrons distributed among 4 orbital shells. Antimony has 15 more electrons than krypton. The first 2 electrons are found in the sphere-shaped 5s orbital shell. The next 10 electrons fill 5 clover-shaped 4d orbitals. And the final 3 electrons are distributed among 3 lobe-shaped 5p orbitals. Only the 5 valence electrons in the 5th level s and p orbitals influence how antimony interacts with other elements. Molten antimony is poured into a graphite mold. As it solidifies, a pinging sound can be heard. This is probably due to the sudden deformation of the internal crystal structure as it cools. Once the antimony has solidified, an ingot is taken out of the mold and hammered with a chisel to reveal its brittle, flaky, reflective, crystalline interior. The ancient Egyptians used a compound of antimony for black eye makeup, and it is still found today in some cosmetics. Antimony is alloyed with lead to increase its durability and hardness. Some antimony alloys are used in batteries. Pure antimony is used to make certain types of semiconductor devices. Antimony compounds are used to make paints, ceramic enamels, glass, and pottery. Element number 52 on the periodic table is tellurium. The atomic symbol for tellurium is Te. Tellurium is a silvery white, crystalline, reflective semi-metal with semiconductor properties. Tellurium gets its name from the Roman goddess Tellus, meaning the earth. Classified as a semi-metal or metalloid, tellurium is located in the periodic table's 5th row, period 5. Each atom of tellurium consists of a cloud of electrons surrounding a compact nucleus that contains almost all the atom's mass. In the most common form of tellurium, its nucleus has 52 positively charged protons, plus 74 uncharged neutrons. Tellurium has 52 negatively charged electrons to balance its 52 protons. These electrons are found in 5 orbital shells surrounding the nucleus, which can be visualized as being built up from the nearest preceding noble gas, krypton. Krypton has 36 electrons distributed among 4 orbital shells. Tellurium has 16 more electrons than krypton. The first 2 electrons are found in the sphere-shaped 5s orbital shell. The next 10 electrons fill 5 clover-shaped 4d orbitals. And the remaining 4 electrons are distributed among 3 lobe-shaped 5p orbitals. Since the electrons in the 4d orbital are at a lower energy than those in the 5s and 5p orbitals, only the 6 valence electrons in this 5th level shell influence how tellurium interacts with other elements. Here we observe tellurium in its metalloid state. A chisel and hammer chip away a small portion to show how brittle it is. In this experiment, a small portion of tellurium is placed into a glass vessel and concentrated sulfuric acid is poured onto it. The tellurium reacts with the acid to produce an ion of tellurium, which creates a crimson color. Here is another beaker with an identical reaction at a later stage. Notice how the solution now has a uniform deep crimson color to it. Tellurium's main commercial use is as an alloying agent. It is added to copper and stainless steel to make them more workable, and to lead for strengthening. Tellurium is a primary ingredient in blasting caps, and it is also used to color glass and ceramics. Its conductive properties lie between those of a metal and an insulator, which means it can be used as a semiconductor in the manufacture of photoelectric diodes in solar cells.
Element number 84 on the periodic table is polonium. The atomic symbol for polonium is Po. A fairly volatile material, silver-gray polonium is radioactive. Polonium's name comes from the Latin word for Poland, the home country of the element's discoverer. Polonium is classified as a semi-metal, or metalloid. It is located in the periodic table's 6th row, period 6. Each atom of polonium consists of a cloud of electrons surrounding a compact nucleus that contains almost all the atom's mass. In the most stable form of polonium, its nucleus has 84 positively charged protons, plus 115 uncharged neutrons. Polonium has 84 negatively charged electrons to balance its 84 protons. These electrons are found in 6 orbital shells surrounding the nucleus, which can be visualized as being built up from the nearest preceding noble gas, xenon. Xenon has 54 electrons distributed among 5 orbital shells. Polonium has 30 more electrons than xenon. The first 2 electrons are found in the sphere-shaped 6s orbital shell. The next 14 electrons fill 7 lobe-shaped 4f orbitals. The following 10 electrons fill the clover-shaped 5d orbitals. And the final 4 electrons are distributed among 3 lobe-shaped 6p orbitals. Since the electrons in the 4f and 5d orbitals are at a lower energy than those in the 6s and 6p orbitals, only the 6 valence electrons in this 6-level shell influence how polonium interacts with other elements. The sound on this record is disturbed by a crackling noise caused by dust on the record. The dust sticks to the record via electrostatic charge. The polonium fitted on this cleaning brush will emit alpha particles from its nucleus, which dissipate the electrostatic charge. Then it's possible to remove the dust from the record with the brush, and the crackling sound is reduced. The highly radioactive nature of polonium restricts its commercial uses. It can eliminate static electricity in some machinery and is used in brushes to remove dust from photographic films and other sensitive surfaces. Polonium has been used as a lightweight heat source for thermoelectric power for satellites because even a small amount releases a large amount of energy.